Hello everyone, my name is Christina and I'm a PhD candidate from the University of Connecticut. In this presentation, I'm going to talk about exploring the management value of a machine learning-based model that predicts chlorophyll-A using multimedia modeling environmental predictors. And before I continue, I would like to acknowledge the people I work with, my advisor, Dr. Astita, Dr. Garcia, and Dr. Vlahos from the University of Connecticut. In past CMAS conferences, we introduced and presented updates on a machine learning-based Chlorophyll-A model for Lake Erie that we developed using explanatory variables from numerical prediction models which are ran at a 12-kilometer grid spacing. The Chlorophyll-A model uses the WRF model for meteorology data, the VIG model for hydrology, and the EPIC model for agricultural fertilizers. The explanatory variables from these models, together with the chlorophyll-A measurements, are fed into our random forest machine learning model to predict our target variable chlorophyll-A. Our work has since then been accepted and is currently in press with the Journal of the Great Lakes Research. In this presentation, we are moving on to the second phase of the project, which is to use the chlorophyll-A model to explore the model's management value. I will only briefly go over the findings of the chlorophyll-A model, but you can read more details about it through our paper from Chan et al. On the right, we see the performance of the chlorophyll-A model's prediction of seasonal chlorophyll-A. Over 80% of the variance in chlorophyll-A measurements is explained by the model. The model also identified eutrophic conditions, which is when chlorophyll-A concentrations are less than 5 micrograms per liter, 94.7% of the time. And in the plot, you can also see the difference in the severity of chlorophyll-A in the 3 different basins of Lake Erie. You can clearly see the western basin in red, which is the most problematic part of the lake, with seasonal chlorophyll-A concentrations of over 50 micrograms per liter. This is expected because the western part of the lake is more heavily influenced by agriculture. Through the chlorophyll-A model, we also ranked the 20 explanatory variables that were used in the model in order of importance using the variable importance plot that you see here. And in this plot, variables with a higher percent mean squared error are considered of greater importance by the model. So for example, the top 3 variables that we see are longitude, average wind speed, and latitude. This is also followed by a list of fertilizer applications, which are basically all sharing similar percent increased MSEs. And we also studied how each variable affects chlorophyll-A by using accumulated local effect plots or AOE plots. Here I'm showing an example of an AOE plot of the layer 1 application of mineralized phosphorus, which clearly shows that with an increase of this form of fertilizer, it would lead to an increase in chlorophyll-A. Again, more details and findings can be found in our article. From our findings, we saw that agricultural fertilizers played an important role in algal growth. So we're now moving on to the second phase of the project, which is to use the chlorophyll-A model to investigate how managing these agricultural fertilizers affects the prediction of chlorophyll-A, which is a proxy for algal growth. And our main objectives are to evaluate how fertilizer application reduction scenarios can impact predicted chlorophyll-A concentrations, and we also want to identify whether reducing fertilizer applications can revert predicted chlorophyll-A concentrations back to healthy levels. I would also like to preface that the work I am presenting is still an ongoing work in progress since we are still at the early stages of the project. Like I said, our study area is Lake Erie, and we're focusing on the United States part of Lake Erie from 2002 to 2016, and we're utilizing in situ chlorophyll-A measurements that have been provided by the Lake Erie Committee Forest Task Group and the University of Toledo Lake Erie Center. These chlorophyll-A measurements are then seasonally averaged for the May to September period, which serves as our response variable. The chlorophyll-A stations across the western, central, and eastern basins of the lake have also been paired with one of the specific watersheds that are outlined in green, purple, pink, orange, and brown. And for this presentation, we will solely focus on this green watershed, which is paired with the stations located in the western basin, which are also the most problematic stations in the lake, which suffers the most from high chlorophyll-A concentrations. And the reason we're focusing on the green watershed is because it encompasses the Maumee River watershed, and it's the area that is most widely affected by agricultural activity near the lake. This is the complete list of variables from WRF, VIC, and EPIC used to train the random forest model. The EPIC variables are shown in green, which include the different layers and forms of nitrogen and phosphorus EPIC fertilizer application variables that have been aggregated spatially for each of the individual watersheds and temporally for the chlorophyll-A season. For this presentation, we will only be focusing on how the reduction of these fertilizer application variables can reduce predicted chlorophyll-A concentrations while all other weather and hydrology variables in the model remain unchanged. We trained the chlorophyll-A model with data from 2002 to 2015, but the fertilizer application reduction scenarios are only applied for the 2016 dataset. Again, our area of interest for this evaluation are the chlorophyll-A stations located in the western basin of the lake. The plot in the bottom shows the 2016 observed versus predicted chlorophyll-A concentrations by the chlorophyll-A model. The observed is indicated by the black bar, and the predicted is indicated by the green bar. In total, there are 8 stations in the western basin, but we will only focus on the most problematic stations that are also well predicted to draw conclusions from our tests. These stations are going to be 7M, 8M, and MB18. In our paper, we also briefly evaluated nitrogen and phosphorus fertilizers from EPIC with survey data from the Nutrient Use Geographic Information System for the entire U.S. Lake Erie watershed, and we determined that EPIC underpredicts applied nitrogen by 9.86% and overpredicts applied phosphorus by 3.59%. For our first scenario, we attempted to identify a realistic amount of nitrogen reduction by investigating the baseline EPIC total nitrogen applied in the green watershed for our study period. And we saw that 2012 was the year with the lowest nitrogen fertilizer applied, with nitrogen fertilizer applications in 2012 being 16.5% lower than that of 2016. And so for this scenario, we're investigating what would happen if 2016 nitrogen fertilizer applications were reverted to its lowest point in 2012 by applying a 16.5% reduction to each of the nitrogen fertilizer application variables paired with 2016. So from this scenario, we see on the left plot the originally predicted chlorophyll-A values for 2016 with unchanged fertilizer values in the black bar, and in the orange bar, we see the predictions for 2016 chlorophyll-A with a 16.5% reduction in applied nitrogen fertilizers. We can see on the right plot the percent change in chlorophyll-A for the 3 stations of interest. We are mainly looking at how the chlorophyll-A model behaves with these changes in fertilizer applications, so not a lot of attention should be given to these specific percentages. But we also saw that stations that are more problematic or have higher chlorophyll-A concentrations tended to benefit the most from these fertilizer reductions, which is interesting because MB18 is closest to the watershed outlet, meaning that it is exposed to higher nutrient loadings compared to the other 2 stations. We also see that even with a 16.5% reduction of nitrogen, predicted chlorophyll-A levels still remain around the same level. We followed the same idea for the phosphorus reduction scenario, and saw that epic phosphorus fertilizer applications seemed to be increasing over time for the green watershed. And we also identified that 2002 was the year with the lowest phosphorus fertilizer applied. In this case, 2002 phosphorus fertilizer applications were 6.5% lower than in 2016. For this scenario, we're investigating what would happen if 2016 phosphorus fertilizer applications were reverted to its lowest point in 2002. So we applied a 6.5% reduction to each of the phosphorus fertilizer application variables paired with 2016. From this scenario, we see on the left plot the originally predicted chlorophyll-A values in the black bar. In the blue bar, we see the baseline reduction for phosphorus, and in the orange bar, we see the baseline reduction for nitrogen. And on the right, we see the percent change in predicted chlorophyll-A based on both the phosphorus and nitrogen baseline reductions. We again see that the stations that are more problematic in terms of chlorophyll-A will benefit the most from the reduction in fertilizers, but we do see that following a phosphorus baseline reduction leads to a smaller decrease in predicted chlorophyll-A than it would for following a nitrogen baseline reduction. But it would be more comparable if we also reduced phosphorus fertilizer applications by 16.5% like we did for nitrogen. So now we're moving into reducing fertilizers at a more drastic and unrealistic level, which has not been trained by the chlorophyll-A model for this area of the lake. So what if the amount of 2016 phosphorus fertilizer applications were reduced by 16.5%? This scenario clearly indicates that a 16.5% reduction in phosphorus fertilizer applications would be more beneficial than reducing nitrogen fertilizer applications by the same amount. However, we also know that this is quite a drastic reduction for phosphorus. So for this next scenario, we explore a combined reduction of both phosphorus and nitrogen at their baseline levels. The yellow bar shows the results of this scenario, and we can see that for the more problematic stations like 8M and MB18, we see that a combined baseline reduction of nitrogen and phosphorus would lead to the scenario with the best decrease in predicted chlorophyll-A so far. This indicates that reducing both phosphorus and nitrogen fertilizer applications is more beneficial than only focusing on reducing one type of fertilizer. However, by just following the baseline reduction of phosphorus and nitrogen fertilizer applications seen, it would not be possible to obtain healthy predicted chlorophyll-A levels that are less than 5 micrograms per liter. In this section, we explore whether reducing any of the 10 forms of epic nitrogen or phosphorus fertilizer applications individually would be an effective way to tackle chlorophyll-A concentrations in the lake. We keep an unrealistic individual fertilizer reduction of 50% for each of the variables for consistency, and for simplicity, I am also only showing the results for station MB18. And this exercise indicates that reducing layer 2 organic phosphorus leads to the highest reduction of chlorophyll-A. And we also see that layer 1 mineralized phosphorus reduction is more effective than layer 2 mineralized phosphorus reduction. More research will be necessary to understand the significance of this scenario. However, this scenario shows that the drastic reduction of solely one variable will not be enough to reduce predicted chlorophyll-A substantially, since some of these drastic reductions in fertilizers perform worse than the baseline reductions. This further strengthens the fact that reducing groups or combined forms of nitrogen and phosphorus fertilizers is more effective than reducing only one type of fertilizer. For the final scenario, we explore 5 different combined reduction strategies: a 10% combined reduction of both total nitrogen and total phosphorus at the same time, and so on with 20%, 30%, 40%, and 50%. This exercise shows us that no matter how drastic or unrealistic the reduction of fertilizers are, we will not be able to turn predicted chlorophyll-A levels back to healthy levels, but it is definitely possible to control chlorophyll-A concentrations and make algal growth less problematic and intense with even a 10% reduction of fertilizers. These are some of the limitations in our study. There are differences between the actual number of fertilizers applied versus the predicted EPIC fertilizer applications. We're not considering the synergistic roles that meteorology and hydrology play in affecting the fate and transport of these fertilizer applications and the prediction of chlorophyll-A. Our current fertilizer application management scenarios presented are only theoretical and would be difficult and unrealistic to attain, and our current scenarios conducted are low in granularity. Since this is still a work in progress, for now we are only considering the effects of fertilizer reductions in one watershed for the western stations only. We do not consider changes in cropland use, for example, an increase or decrease in corn production, and we only focus solely on fertilizer reduction when we could be exploring other agricultural management practices such as till versus no-till farming. In summary, for our ongoing work, we found that more problematic chlorophyll-A stations will benefit the most from these fertilizer reductions. We also found that reducing only phosphorus fertilizers leads to a higher reduction in chlorophyll-A than reducing only nitrogen fertilizers. However, a combined reduction of both would lead to the best results. And we also found that even with a dramatic reduction in fertilizers, it is not possible to achieve chlorophyll-A concentrations less than 5 micrograms per liter. However, it would be beneficial in lessening the intensity of algal blooms. And for our future steps, it would be necessary to first establish a connection between the change in fertilizer applications and nutrient loadings in the tributary. And we will investigate how a change in crop production would affect chlorophyll-A concentrations. We will also have to further investigate the balance between fertilizer reductions to improve water quality versus the effects it would have on agricultural management. And last but not least, we will incorporate climate change scenarios such as increases in temperature, changes in precipitation, and so on. I would also like to thank everyone who has made this work possible, and I would also like to thank you for your attention.